We now want to be able to use some rational function operations to help us in finding some antiderivatives. So when we have, we want to find an antiderivative of a rational function for which basic substitution is ineffective, or basic trig substitution is ineffective, we can often use some algebraic techniques, specifically long division and or partial fraction decomposition, to turn the integrand into sum of functions, producing a sum of integrals that we can solve using earlier techniques, usually either with a simple substitution or in some cases a trigonometric substitution. So before we go on to finding antiderivatives of rational functions, we're going to first review some rational number and rational function operations. So in this one we're going to review a few basic things, and we'll actually have a series of these little videos reviewing certain operations. So you should have first seen these algorithms, most of them in elementary school, when you applied them to basic constants, rational number arithmetic, in other words, fraction arithmetic. So basically the same algorithms that you learned in elementary school, maybe upper elementary, for fractions are the same algorithms that are used for rational functions, and the same operations you use for integers are very similar to the ones that are used for polynomials. So you should have seen these algebraic techniques in your algebra and pre-calculus classes. However, it's my experience that most calculus students would benefit from a refresher on these operations. So let's take just a little time to review some basic material now. First of all, let's talk about multiplication, the long multiplication algorithm. We multiply polynomials using the same algorithm that we use to multiply multi-digit numbers. The thing that makes them work is the distributive property. We use the distributive property to multiply each digit of one factor by each digit of the other factor. And we carefully line up the like digits in place value, then we add the place value digits together to get our final answer. Multiplying polynomials uses exactly the same technique. Terms of one polynomial and then correspond to digits of the natural numbers. So we multiply each term of one polynomial factor by the terms of the other polynomial factor. We are careful to line up like terms, and we finish by adding together like terms. So here's an example on the left using just numbers, constants, integers. 132 times 23. 2 times 3 is 6 ones, which goes here. 2 times that 3 is 9, but that's actually 3 times 30, so that's 9 tens, which goes in the 10 spot. And 3 times 1 is 3 hundreds here, so that goes in the 100 spot. This is a 20 times 2, so that's 2 tens, so that goes in the 10 spot. I need a 0 for a placeholder. 2 times 3 is 6, but that's really 20 times 30, so that's 6 hundreds, so that goes in the 100 spot. And the 2 times 1 here is 2, but that's going to be in the 1000 spot. And we would just add up. 6 plus 0 is 6. 9 plus 4 is 1 group of 10 and 3 left over, so we put the 3 here. Pulling over the 1 group of 10 with the 6 and the 3 makes a whole nother group of 10, so we 0 placeholder. Bring that group of 10 over here and add to that. When I say group of 10, I mean 10 hundreds, which is 1,000, and add those together. So the answer is 3,036. I'm sure you learned that way back in elementary school somewhere. Then by the time you got to Algebra 1, you should have applied exactly the same algorithm over here. 5 times the negative 7 is negative 35. 5 times 2x is 10x. 5 times 3x squared is 15x squared. Negative 3x times negative 7 is positive 21x, lined up under the x terms. Negative 3x times 2x is negative 6x squared, under the x squared term. Negative 3x times 3x squared is negative 9x cubed. X cubes go over here. 4x squared times negative 7 is negative 28x. 4x squared times 2x is 8x cubed, line up under the cubes. And 4x squared times 3x squared is 12x to the fourth. And then just add up like terms. We have 12x to the fourth. Add these together, we get a negative 1x cubed. Add all three of those coefficients together, it's negative 19x squared, 31x, and minus 35. So that's just basic polynomial multiplication. How about polynomial division? Well, long division works the same as long division Long division for polynomials works the same way as a long division algorithm you learned in elementary school. So let's try this out. So here we have 3 thousandths. There's not enough to get 21, so you won't get any thousandths. We have 35 hundredths, and we want to see how many 21s we can pull out of that. Okay, and so it goes in one time. So 1 times 21 is 21. It's really 2100. And so we subtract then, and we get 146 tens and then 8 more. So we take the 146 tens and see how many 21s we can get into there. The way to check it out is just look at the 2 into the 14. Okay, that would go, we would try 7 times, a little guess and check, but if we do 7 times 21, it's a little bit big. Okay, that'd be 1470, which is too big. So we bump it down to a 6. 6 times 21 is 1,126, and we have a 0 here, because it's really 60 times 21. Subtract 8, 0, 2, and looks like we got 9 more of those. So 9 times 21 is 189. Subtract and we get 19. We know we're done when we've run out of digits here, and the remainder down here is less than the divisor. So a couple of ways this might have been written in elementary school. You might have said that this is the dividend, 3, 5, 6, 8, and the divisor is 21. The quotient is 169, and the remainder is 19. So you could have done quotient remainder. But you might have also done it as this, 3,568 divided by 21, or as a fraction this way. To make it a proper fraction, it's 169 plus the remainder over the divisor. And sometimes we suppress that plus when we do mixed number form. Now, how could you check to make sure this works? Well, you check it to make sure that if you multiply these two together, the 21 times the 169, and then add 19, we're back to the original thing here, and you just check that works out. Okay, the exact same algorithm is what we're doing over here with polynomials. It's just we write these out. 6x cubed minus x squared plus 4x plus 8, that's the dividend. We're going to divide by the divisor, 2x plus 1. Just look at the first term here, like we just really checked the 2 into the 3 one time, and so forth. Okay, so we do that. We say 6x cubed divided by 2x is 3x squared. 3x squared times 2x is 6x cubed, exactly the same. We also multiply the 3x squared times the 1 to get 3x squared. Now this is the part where we need to subtract. Subtract means changing the signs and adding. This is the most often missed step. So what I encourage you to do is write your original signs down as 6x cubed plus 3x squared, then put the change signs and box them in or circle them, and use the change signs to add. The first one will always cancel out completely, even if you have to use a fraction for the coefficient here. And then here we get negative 4x squared, bring down another term. Negative 4x squared divided by 2x is negative 2x. Negative 2x times 2x is negative 4x squared. Negative 2x times 1 is negative 2x. Change the sign from negative to positive and add. This term cancels, which is our whole point right there. This adds up to 6x, bring it down another term. 6x divided by 2x is 3. 3 times 2x is 6x. 3 times 1 is 3. Change the signs and add. We get 8 minus 3 is 5. We know we're done when we've run out of terms and the remainder is less than the divisor. What does it mean less than? It means a smaller degree. So when the remainder is smaller degree than that. And so again, we could talk about dividends and divisors and quotients and remainders, but we can also talk about it as basically mixed number in form, which is going from the division written out this way or as a fraction, and then rewrite it as sort of a proper fraction as a polynomial plus a proper fraction. It's kind of a mixed number form for polynomials. So it's a polynomial and then a rational fraction that is proper. So this one is improper because the degree is bigger in the top. So if the degree, meaning the biggest power, okay, is bigger in the top than the bottom or even the same, then that's an improper fraction. It's just like over here when the numerator is bigger than the denominator. It's okay for a fraction, but it's an improper fraction. It can be made into a mixed number, into a whole number, plus a proper fraction. This can be made into a polynomial plus a proper fraction. Of course, you can check it by multiplying the divisor by the quotient, adding the remainder, and you should get the original dividend. And I'll leave the check to you. Now, here's another example. Maybe you can try this one yourself. Negative x squared plus 8 plus 6x cubed. Divide that by 2x squared minus 4. I do want to warn you that first, you're going to want to write both of them in decreasing order of degree. And if there are any missing terms, you want to leave a blank spot for it so that you'll be sure you're lining up like terms here. Okay, try it yourself. Press pause now. Come back when you're ready. All right, here it is worked out. 6x cubed divided by 2x squared is 3x. 3x times 2x squared is 6x cubed. Negative 4 times 3x is negative 12x. Notice I lined that under the x terms, which there weren't any. So I introduced a 0x. Notice that I've written the dividend in decreasing order 3, 2, 1, and 0, putting a 0 spot in there if there's any missing terms. And this is also in decreasing order. All right, so let's see. This gives us a negative x squared. When we change signs, that's plus, so it's a plus 12x plus 8. Now you take negative x squared, divide by 2x squared, it's negative 1/2. If you get fractions, well, just so be it. That's what we got. So negative 1/2 times 2x squared is negative x squared. These have to be exactly the same to cancel out. And negative 1/2 times negative 4 is positive 2. Change the signs and add, makes that positive, so that cancels, makes this negative. So we got a 12x and then a plus 6. Notice the 12x plus 6 is degree 1, the divisor's second degree. So this is as far as we can go. So the final answer is that this division is actually equal to this quotient, 3x minus 1/2, plus the remainder over the divisor, like that. So in other words, again, you got a polynomial, maybe fraction coefficients, but still it's a polynomial, and then a proper fraction. Multiplying, dividing fractions. Let's do that as well. Multiplying, dividing fractions is essentially the same as reducing fractions. Basically, factor everything you can see. Factor the numerator, factor the denominator, put it in a single fraction. If the fraction is following a division sign, then invert as you're writing factors in a single fraction. If the fraction comes at the beginning or after a multiplication, you leave the top in the top and the bottom. If the problem is a single fraction with numerator all factored, once you get to that point, then you can cancel out pairs of common factors in the numerator and denominator and see what's left. So basically there are only two steps, factor and cancel. Just like simplifying fractions, same thing. Simplifying a single fraction, it's basically the same steps, just factor and cancel. So basically it boils down to a lot of factoring. Again, we use the same steps whether we're talking about constant fractions or fractions with polynomials. The only difference is you're talking about multiplication and factoring in constants versus multiplication and factoring in polynomials. So here we start factoring this down. We see that there's a 5 in common, so that ends in a 5, so it's a factor of 5. And then we break that down. Looks like there'll be a 3 and a 17. Now, you do this with a factor tree on the side. I'm going to leave that to you to work out. But basically do this, use a factor tree and break this down into prime numbers. Same way from the bottom. Now, we just cancel out anything that's in common. And this one, the 3 was what we could cancel. Cancel the 3 here and a 3 here. And so in factored form, this is 5 times 17 over 2 times 3 times 11. Nothing else will cancel. And so it's clear that nothing else will cancel because everything's in prime numbers. 5 times 17 is 85, and 2 times 3 times 11 is 66. In other words, what we did is we took the top and bottom, and we divided the top and bottom by 3. Okay? And we got something that wouldn't reduce any further. Now we know it won't reduce any further if we break it down into prime numbers. Okay, here's another one. A lot more bigger number. more factoring going on, but eventually you get this factored as 2 cubed times 3 squared times 5 times 7. This factors as 2 to the 4 times 3 times 5 squared times 13. And now you just cancel. All three of those 2's cancel, leaving 1, 2 in the bottom. One of the 3's is left in the top when you cancel that. Cancel the 5's that left, leaving a 5 in the bottom. 7 and 13 are still there. That's reduced. Now we just simplify by multiplying it out. 3 times 7 is 21, and you get 130 in the bottom. Okay, that's just reducing fractions. Reducing fractions is the same with polynomials. X squared minus 4 over x squared plus 4x plus 4. The top factors is the difference of 2 squares, x plus 2 times x minus 2 over x plus 2 squared. Cancel these out, and you get x minus 2 over x plus 2. This one, reverse the, well, this is multiplication. Let's go over multiplication over here. So here, the 70 square, 70, you break that down, and the 121, you break it down. 121 is 11 square, 70 is 2 times 5 times 7, 22 is 2 times 11, 25 is 5 square. Now we got it all multiplication, we can cancel. And you can see how that finishes out. If it's after division, we flip it over. So 54 factors as 2 times 3 cubed. 65 is 5 times 13. 1,183, after the division, is flipped up to the top and is 7 times 13 square. 189 is 3 cubed times 7. And there's some scratch work on a side paper where we did the factoring. I'll leave that to you. Here I just collected everything in order. 2 times 3 cubed times 7 times 13. Here I did the 3 cubed, then the 5, then the 7 and 13. And then just went and canceled out. Looks like the 3's all canceled, the 7's all canceled, one of the 13's, leaving a 2 and a 13 in the bottom and a 5 in the top, 5 in the bottom, and 2 and a 13 in the top, which is 26 over 5. And similarly down here we have 3 of them. Just factor everything, put it in one fraction. This one here is the first one. This one's in the bottom. This one's flipped, so the 1400 is this factorization at the top. This 1053 is down here at the bottom. 51 is 3 times 17. The 85 is the 5 times 17. And before I canceled, I just grouped things together. I've got 3 2's. I've got 4 3's. Any 5's. There's 2 5's. There's a couple of 7's, a 13 to 17. And did the same thing in the bottom. And it's a little bit easier to see what's going to happen when we cancel. 3 of those 2's cancels with 3 out of there, leaving 1 in the bottom, and so forth. It looks like everything else cancels completely, so it's just 1/2. Okay, same thing works for polynomials. Polynomial fractions, rational functions, rational expressions. So we take this, and here's a multiplication. So we just factor this. We're going to put this in decreasing order, factor out a -2, and then we're left with 25x squared minus 9, which factors as 5x plus 3 times 5x minus 3. X cubed minus 8 is a difference of 2 cubes. It's x cubed minus 2 cubes. So you bring down the x, the minus the 2. To get the trinomial part, you square the first, square the last, multiply, and use the opposite sign on the middle. This one here, we factor a 4 out, or 2 squared if we want to think of it that way. And we're left with x squared plus 2x plus 4, which actually doesn't cancel anymore, doesn't factor anymore. Actually matches this, so it's going to cancel out. And this one is trial and error or anti-FOIL factoring. To get the 15x squared, it's going to be a 5x and a 3x, or a 15x and a 1x. Those are 2 possibilities for 15. We're going to get a 1 and a 15, or a 3 and a 5. They're minuses, so actually one's plus and one's minus. The one that ends up working is this one. So anti-FOIL is a little bit of trial and error. 5x times 3x is 15x squared. 3 times -5 is -15. Here we get 9x minus 25x is -16x. So that checks. Now at this point everything's multiplication, so we can cancel. The 2 and the 4 cancels, leaves a 2 in the bottom that's negative. So I can put the negative somewhere. I'll put it up here. The 5x plus 3's cancel. We still got the 5x minus 3. Still got the x minus 2. But these guys right here cancel. And the 3x minus 5 is left at the bottom. And so unlike the number parts over here, I'm not going to FOIL this back out, multiply it back out, I'm going to leave it factored over here. So here again, x squared plus 4x plus 4 is x plus 2 squared. 3x squared minus 11x plus 10 is 3x plus 5 times x minus 2. The x to the fourth minus 1 is x squared squared minus 1 squared, so that's x squared plus 4 times x squared minus 4. X squared minus 4 factors further is x plus 2 and x minus 2. 2x squared plus x minus 6 is 2x minus 3 times x plus 2. This one is 6x squared minus 19x plus 15 goes to the top and turns out to be factored as 2x minus 3 times 3x minus 5. This one can be factored by grouping. Group the first two, group the last two, factor an x squared out and you're left with x plus 2. Then factor a 4 out and you're left with x plus 2. Then factor the x plus 2 out and you're left with x squared plus 4. Now, actually it turns out every single thing cancels in this one if you look. X plus 2 squared here, here it is, here's one and here's the other one down here. X squared plus 4 is here, here it is. X plus 2 is here and here. Wait a minute. No, that looks like that's wrong. Let me make sure. That's right, that's right, that's right. Looks like we have we have 3 x plus 2's in the top, so I think the answer should be not 1, but x plus 2. Let's keep going. 2x minus 3's cancel, the 3x minus 5 cancels, the x minus 2 cancels, x squared plus 4 cancels, but there are 3x plus 2's, and here I only have 2 in the bottom. So the answer is x plus 2. Okay, I'll let you fix that. Okay, so let's stop there. We'll talk about adding and subtracting fractions a little bit in our next video.